Hello fellas, today we will be talking about a small problem for towers of Hanoi. This problem is also known as towers of Brahma, by the way, and there's a very interesting story about it, which I'll drop to you in the description below. Well, for now, this little 5-minute problem, there are three towers, T1, T2, T3. T1 contains n disks of different sizes which can slide onto any tower. The puzzle starts with the discs in a neat stack in an ascending order of size on T1. So T1 is a tower, T2 is a tower, T3 is a tower. On T1 there are n discs. The smallest disc at the top, thus making a conical shape like this, right? The objective of the puzzle is to move the entire stack to T3, to T3, right? Obeying the following simple rules. Only one disc can be moved at a time. Each move consists of taking the upper disc from the tower and placing it on top of another. That is, a disc can only be moved if it is the uppermost disc on a tower. So top of stack top of the stack of discs gets removed first, and no larger disc can be placed on top of a some smaller disc. So wherever the disc is going, it has to land on a disc which is larger than that, right? So the task is, given a value n, print the steps to be performed to obtain the required arrangement. Each step of your output must be shown as below. Move T1 to TJ, Ti to TJ. So here we are having, we just have to list out our steps as move Ti to Tj. Alright, so the problem says the input is a number n, output is the moves to accomplish the task, and yeah, then we'll be done. So n is less than equal to 10. So okay, this is a fresh problem, I haven't done it earlier before. So what looks like is that, for example, our input is of size 2, so smaller is above, and both are on T1, right? Yeah, as shown here, T1 contains n disks. So n is 2, so T1 and so 2 disks are there. The first task is to move from T1 to T2. So T2 is the auxiliary disk here. We have to move the entire stack to T3. Yeah, as mentioned, this making a conical shape. Alright, fine. The puzzle starts 3 towers. Okay, fine. The objective of the puzzle is to move the entire stack to T3. So from T1 to T3, and T2 is the auxiliary stack which we can use for our purpose, however we like. So from T1 to T2, the output says move T1 T2. So the smaller disk from T1 will move to T2, then move T1 to T3. So the larger disk which is left, the only one left at the top of the T1 stack, it will be moved to T3, and ultimately the second disk is the firstly moved disk which is on T2 will be moved to T3. That way our two level of pegs will be moved from T1 to T3. So in our case, we will be just taking input from, yeah, as mentioned in the program earlier, we have to read from SDDN and print to STDL. So we'll do just that. Scanner SC is equal to new scanner. We'll write a scanner, and we will pass in system.in for taking inputs. SC dot, now we'll read the input. Input is just one number, which is the number of pegs in the T1 disk. So int n is equal to sc dot next int, and now we have the input. Now we will run a recursive printer or of towers of Hanoi, which will take n and move things from uh, tower number, let's call it string t1, right? String, or we can just have the tower as numbers, or maybe identifiers are t1 only. So start, no, this will be just t1 in our case. So t1 to t3, using auxiliary stack t2. Yep, that's it. And this will also do the printing, and we just have to worry about, like, no, okay, we just have to write this function to private static void towers of Hanoi or towers of Brahma, whatever, and we will have int n, string start, string destination, and string aux. Yep. In this we will first run the base case. So the base case will be when we are having n, which is, so after we are having n, which is 0. So if the count of the stack, there's nothing left to do on the T1 stack, or the first stack, starting stack, then if n is equal to 0, then we have to do nothing but just return from our call function call. Else, the recursive case, here we have to take care of a few things. So reducing the problem to just taking one stack at a time, we can see to it as like we have a conical set of pegs on T1, and we want to accomplish moving this stack to the T3 stack using T2. So T2, the pole. So now this can be achieved in this way. We will move the entire stack, but we'll leave the last peg to T2. We'll move the last peg from T1 to T3, and then we'll move the entire elements, or the pegs present in T2 to T3. This is one step lower. So this is the assuming the hypothesis that TOH works perfectly fine. We don't have to question that. We just have to focus on inducing how it will function, how the TOH. So assuming the TOH also works for a smaller problem of one lesser number of pegs, we'll just move. We'll just assume. We'll just induce our problem for the original n number of pegs. So here we go as this. We'll just say otherwise TOH. This works fine. N minus 1. So n minus 1 will work for perfectly fine. Assuming that from start is, sorry, start is whatever start we are given, right? Start. Then we are moving it to destination will be aux, and we'll be using dest in the middle ways. Anyways, any place in the middle. Then we'll print our task, which is current task system dot out dot println. Oops. Yep. And we'll write move. Our task is to write just move T1 to T2. Move space plus T1 here is the start, right? And space plus moving the last peg from start to destination, right? So destination. This is a task of the current move, and then the remainder of the moves from T2 to from the auxiliary stacks to the final destination stack will be moving just uh, 1, moving all the stacks. So n is here. Now n minus 1 will be the one that will be selecting from st, which will be the smaller problem, n minus 1 will be moving from st, which is aux right now, and they will be going to destination using start. This is our function, and here it will work fine. Let's just try to run it once and see what the output is saying. Yo, we passed all the test cases. Let's submit and see. Yep, I do. Oops. Yes, and we passed all the test cases and it's got it. Yoo-hoo! So that was about today's problem, and we'll come back soon. See ya. Ta-da. Bye-bye. Happy coding.